All right, everyone. Welcome to our extra hour, our first extra hour. Now, we're not going to have these every Friday because during exams, we're going to do those on Friday, and I'll use the extra hour to give you an extra hour to do your exams. So we don't actually have that many of these. These extra hours are meant to do answer your questions. Well, we have a slight defect there. Okay. In weeks going forward, maybe email me your questions, and good ones, to be blunt, ones that I'm pretty sure everyone has that are maybe a little on the complex side that I can't answer quickly. I'll do those during these hours. Also, it's generally true that there aren't just that many questions, and I've done this class like 5 times, so I have a whole notebook of stuff to just do on my own, which are probably going to answer the questions you have. Now, these are going to be more heavy into the mathematical stuff because that tends to be where you folks are a little weaker, and that's where you need help. That's why I'm going to do that. Now, remember, I also said a couple of times already that your success is one of the markers of your success is your mathematical abilities. So maybe that's not quite your thing, but we can try to boost that up a little bit because why not? Here we are. So I will not cancel these hours. I will try to use the full time. And again, because of the situation, question and answer just aren't going to happen. We can do a little bit of that, but just for obvious reasons, it's not going to work too well. Now again, I've been doing this class a long time, and I know where you're going to have problems. And because of that, I've designed basically extra hour lectures around that. Now I also want to, last bit, I do not design these lectures to be necessary for answering questions on the exam, and that's where your grades come from. That's not what these are meant for. So I will not it's not like an extra lecture. I mean, it is, but it's not necessary for success. You can skip this and still get an A. However, again, I am going to do problems that will probably be on the exam or very similar to ones on the exam, which is much more likely. So if you want to stick around and watch this, then it's probably going to be better for you than if you didn't, because why not? I mean, if that wasn't the case, I just would cancel. Okay, anyway, so that's my spiel. All right, case in point, what are we going to do today? There is a hard problem on your homework set. And you notice all homework sets, by the way, you have one homework set, but they're all the same. They're all 10 questions, and usually the last question, or questions toward the end, are the harder ones. Easy questions at the beginning. If you are having a hard time answering number 1 or number 2, you're doing it wrong. The first questions in a problem set are easier. The last set of questions, 8, 9, 10, are the hard questions. Usually number 10 is the hardest. That will also be true on the exams. Easy questions at first, harder questions at the end. The importance of that is that if you're very hung up on an early question, you're doing it wrong. Those generally are done in 1 or 2 steps. So just heads up on that. So don't have your head up your rear end about that. And another thing I've seen, you are going to have derivational questions on the exam, and I've seen people turn in 20 steps. Usually 2 or 3. Okay, if you don't have an answer, even for a hard question, by step 3 or step 4, maybe at the worst, you're doing it wrong. What do? Stop working on that question and walk away. Walk away for a while and let your subconscious work it out. But you're trapped. If you've gotten to line 5, 6, 7 and you're not at the answer, you're doing it wrong. You're working in a circle. You're wasting your time. Stop. Take at least a 10-minute break by doing other questions and then come back to it. And you're much more likely to get the answer. All right, anyway. All right, so that's my spiel. Okay, now on your present homework, you have question 10. Now, I've already mentioned to you, you're all going to have different homework sets. There's going to be some overlap of questions because I can't write that many questions. And they're all going to be similar, but not necessarily the same. Irregardless of which version of the homework you have, you've all got something that looks like this. Now let's look at a Maxwell Boltzmann. Let's get a Maxwell Boltzmann distribution, and I won't digital this one because I don't really need to. What I've asked you to do is calculate the fraction or probability of molecules moving faster than a speed. Now, some of you were asked how many molecules are moving faster than the most probable speed, or the average speed, or the RMS speed. All of you got one of those three questions. Now, graphically, let me approach this several ways. Just so you know what you're doing, graphically, I'll do most probable in class. The most probable. Okay. Now, what you are doing to answer this question is you are calculating this area. Now, you know the entire area is 1.0, right? That's because the Maxwell Boltzmann distribution is normalized. So you are looking at the area to the right of the most probable. Some of you are looking at to the right of the most average, which is slightly to the right of the most probable. That is something that we're going to do in the next class to find most probable speed and average speed. Regardless, this is how you answer the last question on the problem set. Now, you might think that the average would be half, right? How many molecules are moving how many molecules are moving faster than the most probable speed or the average speed? Oh, well, it must be 50%. The damnedest thing is, no, it's not the case. This is so crazy. It turns out not to be true. And that's why you need to label your graphs, by the way. Anyway, that's why we have to get college educations, right? You're seniors, you're almost grad students, effectively. And this is the kind of stuff you learn. I mean, it looks like it's half, but I'm telling you, it's not. You're not going to get a half. And that's so weird. Especially, like I'm doing most probable, but the average value, average speed is slightly to the right of the most probable. Now again, I'm going to define that on Monday, the equations for those, but irregardless. The fraction of molecules moving faster or slower than those speeds are not half. So there you go. All right, now how do you define that? Well, it turns out, let's look at the percent fraction going from 0 to the most probable speed. And of course, the way I've defined that would be 0 integral of the Maxwell Boltzmann distribution, where the limits are 0, which the lower limit has to be 0, and the upper limit would be the most probable speed, which is, by the way, it's like the square root of 2 kBt over m. Anyway, you'll see that in Monday's lecture. All right, that's what you have to do. Now, the question says, what fraction of molecules are going faster? Well, given that the whole area of the curve is 1.0, then the fraction going faster than the most probable, which of course is, the lower limit is the most probable, and the upper limit will be infinity. Here's the deal with this. Your online integrators, your online math tools that can do these integrals can't do this integral. I've been using the same website to do these calculations. It's basically the #1 used on the website, the Wolfram website, and that's what I linked to. It can't handle this one. I don't know why. It's like a weird flaw. They've never fixed it. But what I want to point out is that would be just 1 minus the integral from 0 to the most probable. This guy, which by the way, guess what? That online integrator deal can handle this. And as you may have noticed in your homework, I give you instructions on how to use that website. So anyway, when it comes to answering this question, this is how you do it. When it comes to answer, well, what fraction moves faster, it's just 1 minus that answer there. So anyway, it's fairly straightforward. I just wanted to point that out. Hopefully you already knew that. That's brainless. All right, anyway. Calculating Maxwell Boltzmann integrals. We've talked about identities. And you've seen on your homework that you've got a real weird one, right? It's a real pain in the rear. And let's see. Let me throw some integral identities at you at first. Now, this is not the one on problem 10. It's similar, and I'll explain why I'm throwing this at you. Okay, let's do, so you may notice that it looks like Maxwell Boltzmann, that there's like the v squared, the constants are always taken out. Okay, so here's an integral identity that you can imagine. Actually, I think I have this in your problem set. Okay, so For answering number 10, it would be nice if this was the right identity. You notice that this is not the identity. Let me explain why. The most important feature I see is that the upper limit is infinity. Remember that the answer has the limits applied. When the upper limit is not infinity, as in this case, you're not going to have this identity. So that's why this is not correct. The one that you have is, of course, kind of hideous. Now, here we go. We got from 0 to something that's not infinity, which we call C. And that's what I found online, by the way. X squared e to the minus ax squared dx. Like I say, yeah, it really looks... Notice that we see that there, but then you get this other stuff, this thing called an IRF. And what I'm going to do in this lecture is explain what IRF is. That's mostly my purpose today. IRF is a very important thing in statistics, and that will become very obvious in a minute. And also, so here's the identity, which is like, right? So I want to just explain this. This is the point of today's lecture. I'm going to get you really used to integral identities. We're going to look at where they come from. I'm going to get you used to IRFs. IRFs are very important in statistics. You should know, you want a college degree in STEM, in a STEM discipline, you need to know what an IRF is, and I bet a lot of you don't. Okay, so that's today's lecture. All right, so what is an IRF? An IRF is... And I see I'm still not using the board too well today. So I'm going to define IRF. IRF is just a function. It's like sine. If you think about it, you're very comfortable with sine and cosine. But what is it? Is sine e to the minus x? Of course not. If sine was e to the minus x, it would just be called e to the minus x. Sine, actually, what your calculator does is it actually uses a really complex Taylor series. Whenever you type sine of pi or whatnot, your calculator is using a complex Taylor series. So I'm just pointing out to you that some things are not as straightforward as you guys would like. So IRF, the function IRF, which a lot of calculators have IRF, not simple ones, but like statistical calculators, financial calculators have IRF. The way that that works is that you just would find the IRF button and type IRF of 1, something like that. So it's fairly straightforward. Just like you do with sine. What's sine of 1? Okay, anyway, so this is the definition of IRF. Notice that it is the area, by area I mean integral, of e to the minus x squared. E to the minus x squared is our bell curve, right? So bell curves are very common in statistics. I talked about that. I think I've talked quite a bit about bell curves. Bell curves are kind of obvious. So what does this look like? So mathematically, this is what it is. As usual, I like to try to graph things. And I won't digital this one because it's kind of simple. Okay, again, bell curves are very important in statistics, which I don't even think I need to prove or talk about. And what this IRF is, it's a constant, and the integral is just an area of a bell curve up to point C. So it's the area of that bell curve. Okay, so there you go. What does the IRF function look like? Here, I'm gonna just graph that, and maybe I'll digital this one in. But I'll have to give myself something to work with here. 2, 4, 6. Okay. What happens is you can see that if C goes off to infinity, then you've just got half the area of a bell curve. And it turns out with these constants, that ends up being just the number 1. So it looks like that. Now it's symmetric. So there you go. So it looks like that. -2, -4, yada, yada, yada. And again, I'll just digital in something that looks a little bit nicer than that. Anyway, so there you go. Basically, IRF turns to 1 once whatever, IRF of whatever, IRF of infinity is 1. So let's take a look back at this equation right here. Let's see, does this equal that if C is infinity? Well, it has to, because okay, I've got square root of pi over 16a cubed, square root of pi over 16a cubed. I've just showed you that Earth is fed infinity is 1, so that's 1. So I have the same term there. Okay, what about this guy? I see e to the minus c a squared, doesn't matter what a is. If c is infinity, I've got e to the minus infinity squared, which is 0. So this sure enough is that. If c was infinity. Okay, so all of this makes sense, and this is what Earth is. Now again, you can imagine that this is very important in statistics, for obvious reasons, because bell-shaped curves are very important in statistics. All right, now what? Oh, I'm going to keep track of time. Let's see here. Sorry, problem with the camera. Anyway, so now what I'm going to do here is just bring those constants over to the right. This will be a little bit easier for what we have to do, which again is to prove. See where that identity on your problem set comes from. So I just brought the constants over to the right. Okay, now in terms of figuring out where that identity of your problem set comes from, the first thing I note is, I'm not going to write that whole thing out, I'm just going to point out that on your homework identity, you have an upper limit that's not infinity, but where it's different than the above is that instead of e to the minus x squared, you got e to the minus ax squared, where a, of course, is going to be, Maxwell Boltzmann m over 2 kBt. Well, how big a deal could that be? A big deal. All right, so this is kind of hard to take care of. So how do we use this to answer that? When there's only a little freaking a in one of the terms. How much could that matter? Well, the answer is it matters a hell of a lot. Okay, what you do is you do transformation of variables. And I know you had this in calc. And just like then, it still sucketh. So how do we deal with it? Now, the trick is that if I've got e to the minus of variable squared, I want to do the same thing. So I'm going to have e to the minus, e to the minus x squared. I'm going to have e to the minus y squared, in which case I can use my Earth identity. I just have to make sure that, I have to understand that y is equal to ax squared. So these start out simple enough, but where you get some problems, and again, we're just building those math muscles. I'm not going to have a problem like this. We're not going to be doing this on a test, all right? Again, this is just you getting good at mathematical this and that. Okay. So, what you do for any function is for an integral f of x dx, and this is on your, this is on the exam, this part's on the exam, but similar problems in this one. And we're going to talk about this in the next hour, but I want you to go ahead and see it now. What you're going to do is, first we look at how we're going to transform variables, and let me put it like this. We're going to say that x is some kind of function of y. X is a function of y. We're going to call that g of y because I'm integrating f of x. Okay, so when I do that, then this integral, which is a function of x, is now a function of y by plugging in g of y wherever there's an x. So as it pertains here, g of y would be, let's see, y squared over a is equal to x squared. So I would take the square root. There we go. See what I did? I said, I brought over the a, I said x squared is equal to y squared over a, so then I just took the square root. Okay. Now, wherever I see a function with an x, wherever there's an x, I write y over the square root of a. Right? So let me simplify it. So you see how easy that is? Right, so when it comes to, let's see, f of x, this is f of x, because g of y is x. When I give you this information, the only hard part is solving for x. And when you do that, wherever you see an x, you write that expression here, y over the square root of a. I know that was a bit of a blah, 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 but look, it's really not that hard, right? Just spend a few minutes with it and you'll get it right. Okay, so that's half the credit for those questions. Then you get this part. dy dx dx. All right, so you see why we're doing that? I've already pointed out that integral of f of x, this is the integral of f of x, but then I've got partial x. I still need a partial x. Sorry, I made a mistake. Speaking off the cuff. Okay, there we go, sorry. You see, I've still got partial x. I take partial x, divide by change in y, multiply by change in y. So I still got the integral of f of x dx. All right, but when I multiply and divide by the partial of y, now we've talked about this before. An hour ago, this is the Jacobian, and we have to deal with that. Okay, so what is the Jacobian? The Jacobian in this case, let's see, if this is dx dy, well, x doesn't have a y in it, but g of y has a y in it, and x is g of y. All right, see what I just did? dx dy is the change in g of y with respect to y, which is y over the square root of a. The change in that with respect to y, which is 1 over the square root of a. See that? Right? This is really quite easy. All right, so now what? Okay, so that's really, in this case, here I'll just write that down. F of g of y, bunch of parentheses, 1 over the square root of a. Okay, so we're making progress. All right, the next thing to do is we have to now worry about these limits. Okay, how do we do that? All right, so next subject, limits. Okay, the limits, remember, limits have the units of the partial. So when I'm going from 0 to c, that's in terms of what x is equal to. Okay, so if x is 0, therefore y is what? Because this guy is the partial of y. All right, let's look here. If x is 0 and x is y over the square root of a, then y is 0. Right, that's pretty easy. If x is c, that's the upper limit here. Sorry, let me put this here. All right, so if x is 0, it's the lower limit of x is 0, then the lower limit of y is 0. Sorry, I got ahead of myself. Okay, upper limit, x is c. Okay, if x is c, y is the square root of a times c. All right, look right here. If x is c, y is the square root of a times c. Here we go. Ta-da! All right, so not too hard. Okay, so now let me put all this together. Now, f of g of y, let's see here. Now, g of y is y over the square root of a. Okay, so, so wait, what have I done? So sorry, I'm working here. My bad. Turning this into a function of y. Sorry, I got a little lost there. Okay, so y squared is ax squared. So this is e minus y squared. Lower limit is 0, upper limit is square root of a times c. And then I've got 1 over the square root of a, which is a constant. Okay, there you go. All right, now, this is pretty easy. What is this equal to? Well, let's take the constant, bring it out. I put myself into a bit of a corner now, haven't I? Okay, so the constant comes out, and I'm left with e to the integral of e to the minus y squared dy, which I can look at this, and I can see that the answer, let's take the constants out because those are brainless, square root of pi over 2. Okay, and then I've got earth of the upper limit. Earth square root of a times c. There you go. Okay, so again, remember, I had this identity, but this wasn't like my problem. My problem is not e to the minus x squared, it's e to the minus ax squared. And that a ended up causing a hell of a lot of problems, didn't it? God. Anyway, by substitution of variables, and we're getting good at math, that's the point, I'm able to figure out that this is how you change ERF. So you picked up a constant, went over the square root of a, instead of ERF of c, you end up square root of a times c. Okay. Now notice that this looks a lot more like the identity that we're trying to get to, right? There's the ERF of square root of a times c. Okay, but you may notice that there's a second term, and these constants aren't quite right, so what's wrong? What's wrong was I was integrating e to the minus ax squared. Now we have to deal with that x squared. That's the last complication we have to deal with, and of course once we deal with that, then we're going to derive this identity. So how do you do that part? All right, I have to wipe out the board, but the answer is integration by parts. Give me 1 second, let me wipe out the board, and we'll be right back. All right, folks, I'm back. Now let's just take a little breather. I know that was a bit much, wasn't it? All right, let's take a breather and see where we're at. All right, we wanted to use this identity on that problem for number 10. The first issue is the upper limit is not infinity on the problem on number 10, so we cannot use this identity. All right, now let's look here. This is the problem set the one we just did. We talked about ERF, and what we've done is we've modified our definition of ERF. Instead of having e to the minus x squared, what happens when we have e to the minus ax squared? So what that does is it modifies the definition of ERF in exactly this way. You end up with a different constant in front, and you end up with ERF instead of ERF of c, you end up with ERF square root of a times c. Okay, so we just did that. Now remember that our goal is to get to this. This is the identity on your problem set of number 10. Now, the way that these are different is that this has an x squared and this doesn't. Okay, so once we handle that part, we're going to be able to derive that identity. How do you do it? Well, obviously we have to take care of x squared. And what I'm looking at here, I'm looking at two functions. I'm trying to integrate two different functions of x. And maybe we could look up an identity, maybe we could use an online integrator, or we could do it the hard way and flex math muscles. God, I hate saying that, so corny. But anyway, let's do that. Let's do integration by parts, right? When you have to integrate, something where you can identify two different functions multiplied, you're going to do integration by parts. All right, so maybe you've forgotten what integration by parts is. So, of course, I use a lot of shorthand. Not too hard to understand, right? So what is integration by parts? You have two functions, f and g, but one of them is the derivative. You get this from the product rule, by the way. In your little silly textbook, excuse me, that I wrote, I show you where you derive this from. Okay, remember that the little dash means that's the derivative. Okay, so again, this is just derived from the product rule, and you integrate it, and you do a derivative and integrate it back. So it's not even hard to derive this, but maybe you remember this from calc class. Okay, so what? So what we have to do is we have to map this onto this, right? This is, we've done this, now we're doing this. We're just trying to go from here to here. Okay, in that case, so what? Okay, we have to figure out what's what. Now, I would like to say f of x is x squared. That would be sensible, but that's actually not the answer. What you're going to do is you're going to say f of x is equal to x. All right, now that makes the derivative of x. And I want to remind you that when that little dash, I was not your calc teacher, so I don't know what you know or don't know, but that little dash means derivative, and in this case that would be just one, right? Okay, so that's easy. All right. Next aside, that means that the derivative of g, I know this is a little funky how you do this, but the derivative of g is x e to, looking here, x e to the minus ax squared. And the reason that you divvy up that x squared between f and g, the derivative of g, is because when you need to integrate this thing, and the way I always do integrals in my head, when I'm integrating this to get the function g of x, what I'm doing is I'm trying to think of the derivative of what is equal to this. I think a lot of people do integrals that way. All right, so again, if this is the derivative, I need to know what g is because that's in my formula for integration by parts. And what is it? It's very straightforward. You can just double check. Again, I'm kind of doing this in my head. What you get is minus 1 over 2a e to the minus ax squared. So if I take the derivative of that, e to the minus ax squared stays, and then you take the derivative of the argument, which of course would be minus 2ax. Yeah, sure enough, it works out. All right, so I've identified, I'm using integration by parts. I've identified f, f prime, g prime, and g. So that's everything I need to now work this thing by integration by parts. All right, so what do I get with that? Now we just had a bunch of algebra. Okay, so I'm going to leave this. Hopefully you can see this. I'm going to work over here because this is going to take, this takes about the whole board, by the way. Again, I hope, mostly, again, I can't emphasize enough, I just want you to get comfortable with these kinds of really kind of hard mathematical stuff. And I assure you that the exams are nothing like this. So why am I doing this? Well, that's because if you can handle this now, what's on the test will be very easy. And I'd be fine to give everyone A's. All right. Okay, so this is the integral. All right, what is f? F is x. And then g, that's why I had to integrate this thing, over 2a. E to the minus ax squared. Now, a little subtlety of integration by parts is that this term, you actually, when you're doing a definite integral, you have to apply the limits. So there you go. All right, now, you know, and one thing I never could quite get over is how integration by parts takes an integral and makes it bigger. It's like makes it worse, right? Yeah, kind of, but it does give you an answer. See, the thing is that now I have to see whether I can answer that integral. And guess what? You can. That's a standard identity. Okay, regardless, let's do this guy. What did we get with this? Okay, upper limit, minus c e to the minus ac squared over 2a. Okay, then minus the lower limit, but that is 0 times blah, blah, blah. Okay, so the lower limit is 0. Okay, so that guy is set, and notice that that is actually this term right here. Halfway done. Okay, now we got to do this one. Okay, what is that? All right, so now we got to do this guy. Let's see here. How do we do this? Okay, now, as usual, I will take out the constants, because why wouldn't I? That always makes everything much easier. E to the minus ax squared. And let's see here. And I've got this right here, right? So that is minus 1 over 2a. 1/2 square root of pi over a, earth, c square root of a. There we go. Okay, now I know that I'm just using the word terribly. Here, let me try to make this a little bit coherent. Let's see, that is 1/4. Let's see here, hold on one second. Pi. 4 into a square root is 16. A squared into the square root times a is a to the third. See that? See how that worked? C times square root of a. Okay, I'm reversing the order, minus c. Squared over 2a. Okay, which is the same as the identity in your problem set. So there you go. All right. So again, I'll work a problem. We're not quite done yet. Maybe we'll end a little early, but let me work a problem. I just want to point out that we started out with a very simple explanation of, I deleted it, but anyway, we started out with a very simple explanation of an ERF. An ERF is very important in statistics. It's the area under a bell-shaped curve, which, as we all know, bell-shaped curves are common probability distributions. Integrals of probability distributions are probabilities. ERFs are very important in statistics. That's quite obvious. We started out with a simple definition of an ERF. We added a slight layer of complication, and then we made it look like the Maxwell Boltzmann by throwing in an x squared, which we solved integration by parts. And now this crazy identity that looks like, what the is that coming from? You know where it came from, you just derived it. You can derive identities starting out with a couple of simple little bits, right? Okay, last bit, let's use it. Let's use this thing. Let's use it on the Maxwell Boltzmann. Now again, actually I think I have a little bit of time, so I'm going to do a Maxwell Boltzmann question, and then I'll give you a little bit of an extra hint on number 10, because I know how most people get that question wrong. I tend to ask this question over and over again. Let's see, what do I want to do? Let's do Maxwell Boltzmann, but I will use an upper limit of infinity. So C is infinity. Okay, so I've got 4 pi m over 2 pi kbt to the 3 halves. B squared e to the minus mv squared. Okay, now as usual, get rid of the constants, but don't forget to add them later, because otherwise that makes you stupid. All right, 0 to infinity, b squared e to the minus mv squared over 2 kdt. My k looks awful. I have to fix that or the world will explode up. All right, so there we go. All right, so again, this doesn't look too bad. All right, now let's apply the identity above. Okay, again, it has all the proper, you're not applying any limits to this. They've already been applied. What you have to do is recognize, for one, don't forget your freaking constants. Number 2 way to miss the problem. Okay, now A, when we map the identity onto the problem, we have to identify what A is, and again, you have to do that like a zillion times. A is m over 2 kbt. Okay, so I've got pi over 16 m cubed kb t cubed 1/2. Is that right? Is that, I've got to make sure I'm not completely messing this up. Yeah, there we go. And, yeah, okay. Now, ERF of C times square root of A. ERF is now ERF of infinity. By the way, here's what you can do. Let me give you some hints from your homework. This C is going to be your velocity. Now you have different velocities. All you have slightly different homework, so be aware of that. But when you multiply this velocity by the square root of A, which of course is square root of m over 2 pi kbt, you're going to end up with an ERF of a number, like 1 or pi. To answer what that is, type it into Google. Say ERF of 1, and it'll say, oh, it's a half, or whatever. So you can do that. Now you can also type ERF of INF, infinity, and it will tell you 1. Okay, so ERF of infinity in this case is 1. All right, now what is this? Let's see here. Now C is infinity, so I've got infinity minus infinity, which is bad, times e to the minus infinity squared. Type it into Google, whatever, it's 0. Okay, so this is the answer. Now again, if you forgot the constants, you're going to blow it, but if you do remember the constants, then let's see, what are you going to get? You're going to get the number 1.0. All the constants will cancel. So there you go. But notice that if you're like, wait a minute, why did we get 1? Why didn't we get the average something something? I've just integrated the Maxwell Boltzmann from all possible limits, and you should get 1.0, which means that a molecule either is moving or not moving. So I should have gotten 1. I just verified that. We did this in a previous lecture. I'm just using this different identity, but this different identity does have to give the right answer. Okay, that's about all I wanted to go over today. Again, let me just give you a hint on the homework. You're going to have an earth, but when you've done this correctly, when you identified A, which I've done for you, and this is given to you, you're going to have earth of a number. Now notice you're going to have the same thing happen here. You're going to have e to the, notice how e to the ac squared is actually the square of this. So if this turns out to be 1, then this is e to the minus 1, right? E to the minus 1 is like 1 over 2.7 or something. So this is a number. Now, if you, when you're applying this, notice that you've got a c over a, which may end up being like square root of kt and all that. And if that's in your final answer, you've messed up. You should get a finite value. You should get like 0.47 or 0.52, something like that. Not square root of kbt. If you find you've gotten the square root of kbt or m or whatever instead of a number, you've messed up. What did you mess up? Constants. You forgot the constants. When you add the constants, here and here, the c over a, or 3 halves, a to the minus 3 halves, those will go away. And you'll end up with like pi or something, a number that you can plug into a calculator. All right, folks, that's it. So these extra hours are going to kind of be like this. I think they're not going to quite be this heavy in terms of mathematics in the future. But I will try to focus on homework problems. I'm just going to go into great detail. And I did drop a fair number of hints that should allow you to do that. And this is how we're going to basically proceed from now on, except during homework weeks, in which case we'll do exams during the extra hour to give you some extra time. So enjoy the long weekend. I will see you on Monday. Wednesday. All right.